Okay, everybody, we really appreciate being here. Thank you so much. We were told not to design an entire engine, but lucky for you, we did listen to design an entire engine. So, speaking of engines, let's talk about engine design today. Engine design is notoriously slow, whether it's testing, certification, design, and even worse, tooling design for cast parts can cost hundreds of thousands of dollars and take years, right? Even worse, most aero companies often get stuck with a small amount of suppliers to support this. So, in places like Honeywell, we have laser fusion 3D printing. How can we use metal additive to actually push innovation in this sector? Like you mean ADAPT. This is the modular engine system for UAVs enhanced specifically for fusion additive manufacturing.
ADAPT is a multi-use centrifugal turbojet engine built for low-life unmanned aircraft. ADAPT is designed for additive manufacturing, making our engines lighter, more efficient, and scalable. We want to support mission systems intelligence, wingman operations, and cargo logistics resupply. We modeled our engine after a PBS TJ200. We want to meet or at least beat those expectations.
So this is ADAPT. It leverages industry-certified materials and quality-first principles. All of these converge to a consolidated part count from previously 150 down to 15. It simplifies in-field maintenance and reduces the need for an extensive supply chain. So more specifically, we apply DFAM principles to every single part you see there, like maximizing self-supporting features, eliminating opportunities for in-trap powder, and ultimately accounting for downskins for surface roughness. Now, what makes our approach different is utilizing NTOP. This makes use of the benefits exclusive to additive manufacturing. NTOP helps you reshape parts for their environment, it helps you generate TPMS and lattice structures, and optimize fluid flow for fluid performance.
So we used the help from Honeywell engineers and NTOP to design some innovative features that aren't really accessible on a typical conventional engine. This includes internal thermal management systems, sound acoustic mitigation, and also topological optimization. So the first one is going to be our integrated thermal management system, where we're taking air from the diffuser and we're taking air from an aspirated inlet guidance vane and pumping it through the outer casing, two different components to get cooled. We're cooling the outer casing itself with transpiration cooling, we're cooling the bearings by running air across it, and then also pumping that cold air onto the hot turbines. We also optimize the lattice structure of the casing to help noise reduction. We're trapping air vibrations in the outer casing to mitigate noise. And then we also optimize the topology for our combustion chamber, as well as some of the airflow characteristics of the inlet guidance vane to have better airflow. All of this allowed us to not only meet specific design requirements, but exceed those of contemporary engines that are competing.
Using tools like DOM and Simulfact, we can rapidly iterate design to boost performance, or integrate technologies like radiative air cooling panels. So they take air from the compressor bleed at 400 degrees Celsius and pass it through the insert cooling channels on the engine casing, and then they're radiatively cooled using a material made out of niobium, yttrium, and copper. It will mostly be copper, and then this helps us cool the hot section of the engine further, like stator vanes and the turbines. So this gives us like a 10 to 15% increase in the combustion chamber temperature, which increases the thermal efficiency of the engine.
Okay, so let's bring it back. That was a lot to hear. First, we used additive manufacturing principles to simplify and consolidate parts of the engine, and specifically more of the static components, right? And then we used NTOP to actually go in and make a system that was as good, if not more advanced, than conventional manufacturing methods. In a broader scale, right, this can reduce complexity, can minimize the amount of failure modes. It also allows you to have direct production link. You don't always have to rely on rigid supply chains, and you can unlock capital in the market of autonomous vehicles, and specifically unmanned UAVs. So, when you compare that versus traditional manufacturing, you'll see that as-printed Inco alloys are about as comparable to cast methods. Other than that, you're going to get, from our research, I want to say it was, I'll say 30% weight reduction, 15% fuel efficiency, and then about in between 5 and 15, depending on where you look, your chamber temperature percent increase. The best part is low upfront capital. Honeywell already pays for the tools needed, right? Other than that, you're saving $800,000 max on your cast production parts. Metal powder is also reusable and recyclable.
Alright, 3 minutes of Q&A with the judges.
I thought this was really well put together, right? I liked how you summarized everything. You know, it starts to get really technical, but you brought it back in to something digestible. Very well, nicely done. I would like to see more, you know, I don't really know much about Inconel, right? How does it really stack up? Do you have a slide or a backup slide where it kind of shows Inconel versus metal? Okay.
So this was just kind of like its actual material properties. Now I understand it's not a lot to say, take my word for it, but I was an intern in the additive lab, and I know that Inconel, even when it doesn't have your traditional post-processing, like it's being densified, is incredibly hard, and it's also very stiff. There's multiple kinds where some are more vibration conductive, right? They're a little bit more ductile, and there's others that are more stiff and can resist impacts, but they'll rattle more. So they are, as printed, pretty good. And the amount of metals that you print as well, you know, titanium, copper, a lot of those are very similar to their cast counterparts. It usually goes cast, and then additively fused, and then rod.
So, question. This Inconel is being used where and where?
So, let's see if I can go up here.
Is there a place where you can use titanium or something else?
I know that, so the reason that we chose Inco in this case was because we've removed so much weight from this, right? Inco's very dense. And so it's very heavy. When you remove weight, you can retain the strength of Inco, while also keeping it light. The better part though is Honeywell's AMTC lab, out of the 20 machines, 18 are Inco. So maybe 15 are Inco 718, maybe 2 or 3 are Inco 625. And so if this was something that you guys actually used and produced, it would be very difficult to pull that out, the powder out of the machine all the time, and it would be 99% of the time, most likely. Titanium powder is also flammable, so it's much more difficult to
Also, Inconel is resistant to oxidation. So when we use this in the combustion chamber, there's no creep damage at high temperature and high pressure.
Okay, so Inconel is for the combustion chamber.
Yeah, correct. In terms of your low cycle fatigue and your high cycle fatigue, things that we talked about before in person, I believe that just with minor adjustments, Inco is kind of a common denominator to all of those.
So we're using 2 specific alloys of Inconel. So the whole section is printed from Inconel 6.
718.
717, right?
718, and the other section is 6.
Yeah, so, and the hot section is printed from another Inconel alloy.
So impeller, shaft, and
That's
turbine-
all traditional, that's all conventional. We're just 3D printing static components. Static components.
However, for low
But Inconel, is that Inconel still? Impeller, shaft, and turbine, is that Inconel?
it is, yes, it's cast.
Cast Inconel. What is that?
You know, I just want to say last thing. I know that with printing for low life and one-way defense kind of mission, we did find that the performance drawbacks from printed surface roughness actually did not matter as much. So in very low life cycles, such as like defense issues, it didn't seem to have as much of a problem as longer life cycle things like multiple trip.
Also, we can run the engine much hotter. So we can run for like 10 hours, but it will have high performance and high thermal efficiency.